Hello everyone. Today we're going to study section 14.8, which is optimization. We're going to talk about a special method. It's called a Lagrange multiplier. So we use this method to maximize or minimize a function subject to a constraint. Okay. Now, this type of problem we did it before. If you look at I think at this 14.6, we try to maximize or minimize a function subject to constraints, and then the constraint is an equation. So we use the equation to write one variable in terms of another variable, okay, and then we substitute into the object function and change the function to one variable or to function of two variables. Remember, one variable, we know how to maximize and minimize function one variable. And then we talk about use a second derivative test to maximize and minimize the function of two variables. But we haven't talked about how to maximize and minimize function with three variables. Okay, so well, I'm going to introduce a method, use a function of two variables, introduce an idea, but the method can extend the function of three variables. Okay, I'm going to use an example to show that. Okay, let's get it started. Okay, so this is our math 1D. Okay, this is a lecture lecture 12. Okay, lecture 12, and then this is a section 14.8. We talk about Lagrange multiplier. Okay. Well, Lagrange is a person. Okay, that's the name of a mathematician, a French Italian mathematician. Okay, we use his name to name the method, okay, because he created this method. Okay, now when we try to maximize a function, we call that function objective function. So here we have an objective function. Okay. So this, well, here I use a function of two variables, f, x, y. So it's easier to see geometric meaning. Okay, we say this is a function. We say the function to be maximized or minimized. Okay, to be maximized or minimized. That function we call the object function. And then we say constraints. Here, just one constraint. Constraint. Okay, so we said this constraint is an equation. Okay, we say g of xy equal to constant. Okay, equal to constant. Okay, now what does mean constraint? Okay, let's look at the two cases. Okay. Suppose on the xy plane. Okay, so here we have this xy plane. So this is x, this is y. If we draw the level curves of z equal to fxy, so we can draw the, say for example, suppose those are the level curves. Well, that's part of it. If you think about it as a mountain, and then you should have closed curves. Okay, so for example, we said this is f equal to 5, f equal to 6, f equal to 7, and f equal to 8. So that means from above to the bottom, that means the function is increasing. Okay, so this is the level curve. We let z equal to constant and then keep increasing. So then, say for example, we say z is a function of two variables. The geometric interpretation is a surface in the space. And then if I use a horizontal plane, z equal to constant horizontal plane to cut the surface, then you're going to have the curves. Now you project the curve on xy plane, and then you got this so-called counter map. And then we say, well, those curves on the xy plane, we call it level curves. Okay? Now, we say we have another curve on the xy plane. So for example, suppose the curve looks like this. And then this curve is g of x, y equal to k. Now, when you want to find the maximum value of f subject to g, so that means you want to find the x value, y value on the curve g x y equal to c equal to k, and then at the same time f be maximized. Now you can see, well, this point give you the maximum value. This point, because you don't have anything below that curve. Okay, still on g. Okay, and then you see if you go down, the f value is increasing, so that's the maximum value. Okay, maximum value, which means those two curves touch each other, or we say they have the same tangent line. So if I draw a tangent line like that, draw a tangent line like that, and then we say, well, the tangent line like this, so we say the gradient vector for each function, okay, should be parallel, maybe pointing this direction, well, maybe pointing the other direction. So that's possible. Say here, this one, or this one, or this direction. Okay, we said that's the gradient vector, which means what? Which means we have this. So here, okay, so here we have this. We say at, so if I call this point P, we say at point P, f is maximized. Subject to g equal to k. Okay. Now, another case, if you draw this way, well, here, how about we say like this? Okay. Another situation. Okay, so if we say, well, still we have a curve like this. So suppose this is a level curves. Okay, suppose we have those level curves. And then suppose, again, this is f equal to 5, f equal to 6, f equal to 7, f equal to 8. And then if I have a constraints, okay, the curve looks like this. Okay. Okay, the curve looks like this. So here we say, well, yeah, I think it's a curve like this. So we say, well, suppose this is g of x, y equal to k. Now you can see in this case, okay, you see when you move up, the functions are decreasing. Okay, so you wanted the x, y value satisfy g and be minimized. So that's this point. Because any point lower than that, the f is larger. Okay, larger value. And again, at this point we have this. We have the both curves have the same tangent line. So for example, like that. So same tangent line. Okay. Well, now, so here we say, yeah, I think I say here, let me point out that because we say, so here we say the gradient vector perpendicular tangent line. So that means may point it this way. Well, you see for f is pointed this way because gradient vector pointed to the direction function increase most rapidly. Okay, and then they and a g, okay, here we don't know. They can't point this direction or point in this direction because here we only draw one g. If you have a more g, the g equal to constant, we don't know whether it's move up or move down. Anyway, so here we have this, so the gradient vector we know of f and g should be parallel to each other. Okay, at least we can say that. So here is, this is, say we say at, still call this point P. At point P, okay, well, of course, if I call this x0, y0, okay, we say f is minimized and subject to, okay, it's not just minimized, it's minimized subject to g equal to k, subject to g equal to k. Okay, now you see the condition is this. We say, well, both cases, okay, we say at x0, y0, that's point P. We say f and g, okay, let's say f and g share the tangent line. Tangent line. Now this implies their gradient vector at that point must be parallel to each other. Well, what do we do parallel to each other? We say is proportional to each other. Proportional to each other, so one is equal to a constant times another one. If the lambda is positive, that means that in the same direction. If lambda is negative, in the opposite direction. Okay, so this gives us, well, Lagrange said this gives us a method to find the extreme value, we say method of Lagrange multiplier. Well, we use multipliers because later on we are going to look at the case we may have more than one multiplier. Okay, so first of all, let's look at it just one multiplier. Okay, so here we say the method is like this. We say to find the extreme value, okay, extreme values of f, say here's the x, y, subject to g x y equal to k. Then we're going to do two steps. First step, we say solve a system. Okay, the first set of equations is gradient vector of f equal to lambda gradient vector of g, and g of xy equal to k. Now remember this part, if you have two variables, you have two equations. Okay, and then f sub y equal to lambda g sub y, because the gradient vector, the corresponding components must be the same. Okay, and then second part, we just evaluate f at the solutions of step 1. Okay, and then we say the largest is a maximum. The largest is the max. The smallest is the minimum. Okay, well, how about it? Let's look at it, a couple examples. Say here's the example 1. Example 1. Okay, we say use Lagrange multiplier. Use Lagrange multipliers to find the extreme value of, say here's the fxy equal to x e to y, subject to x squared plus y squared equal to 2. Okay, so here we say we solve this. Okay, of course here gxy just equal to x squared plus y squared. and k equal to 2. K equal to 2. So we directly, well, you don't have to use a gradient vector, directly find f sub x equal to lambda g sub x. So this gives us e2y equal to lambda 2x, right? And f sub y equal to lambda g sub y. So that's equal to x e2y equal to lambda 2y, like that. And then we say g equal to 2. So we're going to have this x squared plus y squared equal to 2. Now notice we have 3 equations, 3 variables, okay? The x, y, and the lambda. But we don't have to evaluate lambda. We only need to find x and y. If sometimes we don't need it to find a lambda. Sometimes we use lambda value to find x or y. Okay. Now here we say this is equation 1. This is equation 2. This is equation 3. How about we say substitute substitute 1, which is e2y equal to 2 lambda, into 2. Just replace e2y by lambda 2x. So this is lambda 2y. So that's just give us what? Y equal to x squared. Y equal to x squared. Then, if I substitute y equal to x squared into equation 3 by 3, so we have x squared plus x squared squared equal to 2. Now this one, we can write this as x squared squared plus x squared minus 2 equal to 0. So if you factor out, treat x squared as a variable, so you have x squared plus 2 times x squared minus 1 equal to 0, right? X squared times x squared squared. X squared times -1, negative x squared, 2 times x squared, 2x squared. Okay, added together equal to positive x squared. 2 times -1 equal to -2. Now, x squared plus 2 never equal to 0. So that means we have this x squared minus 1 equal to 0. Well, that means x equal to positive -1. If x equal to positive -1, then, well, y equal to x squared. So y always equal to 1. Always equal to 1. So we have 2 points, okay? 2 points. Then we evaluate f at 1, 1. That's equal to e. And then we evaluate f at the -1, x equal to -1, y also equal to 1. That's equal to negative e. Negative e. Therefore, okay, we say subject to x squared plus y squared equal to 2, we say f max is equal to f at 1, 1, which is equal to e. F minimum is equal to f at -1, 1, which is equal to negative e. Okay, well, you see I put it subject to x squared plus y squared at the front, because without this condition, the maximum value, minimum value of f may not be those 2 values. Those 2 values is unsatisfied this curve, well, which is a circle, x squared plus y squared equal to square root 2 squared. So that's a center, the origin, radius equal to root 2 circle. Okay, so that's find the extreme value with the constraints. Now, let's look at example 2. Well, example 2 deal with the function of 3 variables. Okay, we still say use Lagrange multiplier to find. Okay, you already noticed we use multiplier in the first example lambda, but we didn't even find what's the lambda equal to. Okay, well, of course, once you find the x, y value, you use a given equation, you can find a lambda, but it's not necessary. Okay, to find the extreme value, of f x y z equal to x squared plus y squared plus z squared, subject to, so we have a x fourth plus y to the fourth plus z to the fourth equal to 1. Okay, now geometrically, we can still draw picture. Okay, imagine if fxy equal to constant. So this is a level surface. Well, you say x squared plus y squared plus z squared equal to positive constant as a sphere. So with a different constant, you have a different radius. And then, of course, the radius increasing, function value increasing, the radius decreasing, function decreasing. Now, even though we don't know what the surface looks like for the second equation, x fourth plus y fourth plus z fourth equal to 1, we know it's a surface. That's a function of equation of 3 variables is a surface in the space. So you think about at the minimum or maximum, the level surface of f and the constraint surface should touch each other, touch at one point. If touch at one point, then they should share tangent plane at the point. If they share tangent plane, we know the gradient vector for each level surface as just a normal vector of the tangent plane. If they have a same tangent plane, so the normal vector should be proportional to each other. Well, we said not the same, may not be the same, because they may not be unit vector. Of course, the magnitude may be different. And also their direction may be different because one function increases one direction, another function increases in the opposite direction. That could be true. Well, maybe they increase the same direction, so the gradient vector point the same direction. Anyway, we only know that proportional to each other. So we can use the same idea. This part, if we draw the picture, is a little bit more complicated, but it's possible. So, well, you can imagine. Okay, I'm not going to draw the picture here. So when we solve this problem, okay, we use the same idea. Okay, the gradient vector are proportional to each other. The component is f sub x equal to lambda g sub x. Okay, of course, here we say g is equal to x to the fourth plus y to the fourth plus z to the fourth. And then this gives us 2x equal to lambda times 4x to the third, right? And then f sub y equal to lambda g sub y. So we have 2y equal to lambda 4y to the third. Y to the third. f sub z equal to lambda g sub z. So this is 2z equal to lambda 4z to the third. Okay, so we have this. And then now here g equal to 1, we have x to the fourth plus y to the fourth plus z to the fourth equal to 1. We have 4 variables, x, y, z, and lambda, 4 equations. Okay, but the difficulty is because those are nonlinear equations, so we cannot have the method we solve for linear equation, like a Gauss-Jordan method. We can always find a solution or show the solution does not exist. Now, this nonlinear equation sometimes cause some difficulty. Okay, when we solve it, we need to be careful. Okay, now if you look at this, this implies we can write x squared equal to 1 over 2 lambda. Why? Because lambda cannot be 0. If you think about lambda equal to 0, if you look at the first 3 equations, lambda equal to 0, all the 3 equations on the right-hand side equal to 0, you're going to have 2x equal to 0, 2y equal to 0, 2z equal to 0. So x, y, z all equal to 0. Then you cannot satisfy x fourth plus y fourth plus z fourth equal to 1. So lambda cannot be 0. But x could be 0. Okay, so here we say or x equal to 0. And then this implies y squared equal to 1 over 2 lambda or y equal to 0. Okay, now notice if x equal to 0, y equal to 0, then z cannot be 0. So that's why I use a or. Okay, so here we say this implies z squared equal to 1 over 2 lambda or z equal to 0. Now this one, say here, if you look at this, if x equal to 0, y equal to 0, then you're going to have a z equal to 1. Right? If y equal to 0, z equal to 0, that means x has to be 1. You use g. And then if you look at it, say here, if x equal to 0, z equal to 0, x equal to 0, z equal to 0, then we're going to have a y equal to 1. Okay? So, yeah, I think this is a little bit awkward. Say here is this one, and then here is just this one. Okay? So we look at it this. Now, then x squared, y squared, z squared, if I substitute into this equation, so we're going to have what? We're going to have 1 over 4 lambda squared plus 1 over 4 lambda squared plus 1 over 4 lambda squared equal to 1. Okay? Now, this is easy to solve for lambda, which is equal to positive negative root 3 over 2. Okay, I'll let you verify that. Okay? But lambda cannot be negative because you see x squared equal to 1 over lambda. Okay? So we're going to just get rid of the negative sign. Okay? So here, how about I just write this, say root 3 over 2. Root 3 over 2. Okay? So when lambda equal to root 3 over 2, then we're going to have this implies x equal to y equal, this is a y, equal to y equal to z equal to, then we're going to have this positive and negative 1 over root 3. 1 over root 3. Okay, that's easy to verify. Then we say, or we have x equal to y equal to 0 implies z equal to, actually, we can have a positive and negative 1. Yeah, I think I say here positive negative 1, positive negative 1, positive negative 1. And then if x equal to z equal to 0, then y equal to positive negative 1. Or we have x yz, sorry. When we have a y equal to z equal to 0, then x should equal to positive negative 1. Okay? Now, if you look at this, well, we have many points. And then when we evaluate, because function f is x squared plus y squared plus z squared, so the sign doesn't matter. So we say at negative positive 1 over root 3, and then, well, I think a fourth, let me see, I think I should say this is a fourth root over 3. Okay, fourth root of 3. And a positive negative 1 over a fourth root over 3. Positive negative 1 over a fourth root over 3. So this is equal to 1 over root 3 plus 1 over root 3 plus 1 over root 3. Well, so 3 over root 3, that's equal to root 3. Okay? And then we say f at positive negative 1, 0, 0. You see those all those points satisfy the second equation g. This is equal to f of 0, positive negative 1, 0, equal to f of 0, 0, positive negative 1. Okay, when you substitute this, is always equal to 1. Always equal to 1. Therefore, we say subject to x to the fourth plus y to the fourth plus z to the fourth equal to 1. We say f max equal to root 3. Okay, well, add those points. And f minimum is equal to 1. Okay, so that's this one. The last part of this section talk about, say, if you have two constraints. Okay, if you have two constraints, well, your book even draw a picture. Two constraints, that means you have two surfaces if it's a function of 3 variables. And then I'll let you read that last paragraph. If you have two constraints, then you have two multipliers. Okay, so please read that section. And then, well, the homework we have, I think we have at least one problem with the two Lagrange multipliers. Okay, the method is not hard to understand. When we solve the problem, the difficult is solve the nonlinear system. Okay, because we know linear system, we have a Gauss-Jordan method to solve it. Okay, but nonlinear system, based on different system, we use a different method. There's no uniform method to solve a nonlinear system. Okay, because nonlinear system, that means the exponent of the variable not equal to 1. Not equal to 1, you may have a 2, 3. Well, we already say we have a 2, 4. Also, we have an exponential function, okay, sometimes other functions. So that means the variations are so big, and then there's no uniform method. So when we solve the nonlinear system, we need to think about how to make it easy to solve. Always keep in mind that you don't have to find the value of a multiplier. Okay, you use it to do the substitution to find the x, y, z. Okay, if you have 3 variables. But sometimes, if it's easy to find the value of a multiplier, and sometimes we find the value of multiplier, substitute into equation to find the value of the real variable x, y, z. And then Lagrange multiplier, with the nice thing to think about is, well, we don't need to verify the point we found is the maximum minimum. We just say we found all those points, we evaluate a function at those points, the largest is the maximum, the smallest is the minimum. Okay, now you say, like the second example, we found so many points. Well, of course, we say the maximum value of a function can happen at a different point. But if it's a maximum, well, we talk about this is an absolute maximum, then must be the same. Must be the same. So that means we only have one maximum and one minimum. Now, if you find different values, okay, say if you have more than 3 values, so that means that could be some of them are local minimum, okay, local minimum. And then, well, we the method just tells the procedure, and then we don't need to verify that. We use a procedure to find it, and then we give an answer, okay. So please read this section and then try to do the homework problems. Yeah, I think that it's a pretty exciting method, very interesting. I hope you understand it. Okay, I'll talk to you next time. Okay, bye-bye.